Slight switch of topic. We were trying to use the NumPy operations here and the vectorization that NumPy offers to make code faster. This was basically an optimization. The question is, when do you optimize? And what do you optimize? And usually guessing is bad for that. The way to do it is, before you optimize anything, you should profile. Profiling should be done for two reasons. First of all, so that you don't spend hours optimizing something that only took about 2% of your total time anyway. I had that happening once. I had a summer student who came to me who wanted to port something to the GPU, which is also an optimization in the end. And we worked through the example, and he was really frustrated because he wasn't getting the speed up that he was expecting, until I actually looked at the profile of his original code. And this segment that he was porting to the GPU gave us a speed, or took 10% of the compute time. So it was not really worth bringing it to the GPU. If I had looked at the profile first, I would have noticed. I thought he had, since this was after 6 weeks working on this. He wasn't my student. He just came to me because I am one of our GPU experts. All right, profiling. Python offers several profilers. The C profiler is a standard module. It's built in. It is reasonably low overhead. But it only gives you a function point of view. You can only see function calls in the C profiler. And sometimes that is not enough. If that is not enough, then line profiler may actually be helpful. Line profiler actually does a profile for a function or a set of functions that you define, but it does it then statement by statement. So you can really look which statement in my profile takes the most time overall. The Intel tools, actually both vTunes and Advisor, support Python to some degree. It's not perfect. One of the big problems is that you actually see the Python functions as they look from the C Python interpreter. So they look like C calls, but it's still possible to get some information out of it. And they're improving their relation to Python. So for basic Python codes, they will actually, in the meantime, link it to the appropriate line in Python as well. Olaf told you we are the SimLab biology. So I figured one of the most used codes related to biology on our computers is molecular dynamics, although we are trying to change that a little. This is being recorded, I shouldn't say. So I figured we'd profile a simple MD code. Who has done molecular dynamics, or at least knows in principle what it does? OK, I think for the rest, my explanations will be enough, I hope. So what I do is I have a system of several particles. These particles interact with pair forces. So if I have particle A and particle B and particle C, particle A and B interact, particle B and C interact, particle A and C interact, and the total force on particle A is the one based on the interactions with B and C. So I assume that I can divide my forces up so that I can represent them as pairwise forces. gravitation, Coulomb are perfectly fine examples for that, Lennard-Jones. There are a number of potentials that actually will work for this. So pair force here actually calculates the force between two particles. Force calculates the force on a particle due to all the others. Calculate all forces does this for all particles. All right, now I have my forces. And imagine I have these particles flying around, and there are forces acting on each particle. Then I can, and I take a freeze. I basically take a snapshot in time. I want to go to the next time step. So a small dt onwards. For that, I know from Newton's equations that you may not, but that's okay. I know from Newton's equations that I have two things that happens if I have a force acting on a particle. Well, actually, mostly one. It accelerates the particle, depending on the mass of the particle and the force. All right, so acceleration means a change in velocity. Now, since the particle is already moving with some velocity, I have to change two things: the velocity and the position of the particle. This is actually a numerical integration method. That's what STEP does. And so STEP actually does this moving one time step further, and it calls propagate all variables, which actually then calculates the new velocities, and based on the velocities, then and the acceleration calculates the next position. The algorithm implemented here is the simplest algorithm. I think I did the simplest. I didn't do a leapfrog or something. But that doesn't matter for our profiling exercise. For the profiling, really it only matters I have multiple functions that are nested, and I want to find out which one takes the most time. In my main program, I initialize my particles. The x, y, and z positions, well, I do randomly. And I initialize all velocities to 0. And the mass is to 1. So yes, this is a rather simple system of 1,000 particles here. And my time step is 0.01 in some units. I have to do this repeatedly. I calculate the forces on all particles, I propagate all variables for a time step, and then I continue at the first step again. I do this over and over and over again, and this is the basics of molecular dynamics. Or actually, I could also do this for an astrophysics simulation. I could be simulating star clusters this way. Would follow exactly the same algorithm. So I don't have to call molecular dynamics. All right. So here I did 2 time steps. And you basically see my main loop here. I calculate all the forces, and I propagate all the variables. These 2 time steps took 13.7 seconds, which seems rather slow. For molecular dynamics simulation, the time step is usually somewhere of the order of 10 to the minus 15 seconds. The relevant time scales for biological phenomena start at about 10 to the minus 6 seconds. So I have to do of the order of 10 to the 9 steps. At 13 seconds, that would be pretty bad. All right, so let's figure out where we spend our time. before you do profiling, you actually need to get a baseline. So profiling does introduce overheads. And at some point, the overhead may become so large that your profile becomes meaningless. And that's something to watch out for. But you can only look for this if you know what your baseline, what you program without profile, actually how long it takes. So I did that, and for one iteration, I took 6.56 seconds. All right, so keep those in mind, 6.56 seconds. Now, within a Jupyter notebook, we can use the C profiler by loading an extension and then calling a cell with the now available magic PRUN, profiled run. And this is the result of an example run. So first of all, notice the same routine that we took before now takes 8.561 seconds. That overhead is actually already significant. But OK, we'll live with it. And here you can now see, OK, we did a lot of calls, a million, with a total time of 5 seconds within pair force. Lots of forces also actually in multi-array array. We spend time in the force calculation. This is the time including all the routines it calls. So here the cumulative time is including all the subcalls. And this is its own time. So it's here sorted by its own time, the time that it spent just in that routine. So you can see here force takes another 1.4 seconds. So these 3 routines actually take the bulk of our time. All right. So those would be the routines to investigate. And from the total time that we have here, it seems obvious that we want to investigate pair force first. Now, for that, we can do a line-by-line profiling. The reason I don't do a line-by-line profiling for the entire code is that the overhead would be so large that the results would be meaningless, because you don't know how the overhead is distributed. If it were evenly distributed over all calls, that wouldn't be a problem. But the overhead will generally be larger for those functions that are called more frequently, because I have either timers that I need to start and stop, or even if I use the hardware counters, I have to read them out and store them. So for anybody who's doing performance tools, they know that you have to watch out for these things. And everybody who wants to do profiling should know about this too. All right, but I know now that my pair force actually is what I need to look at first. So for that, I can dare run a line-by-line profile. And notice, we are up to 10 seconds almost. So I wouldn't trust the absolute numbers here. But since all these functions are called about equally often, and it doesn't go further in line profiler, it's actually fairly simple script, it still gives good hints. So 23% are spent just on calculating the distance. Because my force here is a simple 1 over r squared force. I do need the distance. So I spend 23% of my time calculating the distance, and then 69% of my time calculating the forces. All right. So is there a way to speed this up? Well, Let's first look at the distance, because it's actually a fairly simple calculation. And let's see how these individual routines fare when we do the calculation. Now we come back to TimeIt. Here I'm using the cell magic of TimeIt, so with the 2% signs. For those of you who don't remember, if I have 1% sign in front of a magic, it acts only on that line. If I have 2% signs, it acts on the entire cell. So TimeIt exists in both versions. In this version, the first line is actually ignored in the timing. So you can use it for initialization. So here I'm just grabbing one of my values. And here I'm calculating x1 minus x0. This takes 58.5 nanoseconds. OK. I don't think there's much I can do about this. So what about the square? So I take x1 minus x0 squared, 238 nanoseconds, 4 times as long. OK. This is not the only way to calculate the square, though. I could do it like this. And interestingly enough, this is faster than this. All right. Well, I'm still calculating this difference twice. Now, I told you yesterday that you have to be careful with caching and calculating extra values and then getting them from memory. But actually, we would be calculating it very close to where we are using it. So it's not quite that bad. And we are here in pure Python anyway. So what if I actually calculate this first and then square the result or multiply the result? Well, that's actually faster. So in this case, an intermediate value actually does help me get my time for the square down from 238 nanoseconds to 115 nanoseconds. So half the time. Not bad. Now, TimeIt is not perfect, especially for things that are so fast. It does its best by using large loop values, but it does have to fight, among other things, modern processors. This is true for any kind of profiling these days. If you want to do real performance measurements on modern processors, it's a pain. It's worse on your laptops, because your laptop processor is not just optimized for delivering performance. That's only one thing, delivering performance when you need it, but also quickly dropping to power-saving modes. And from a performance tools point of view, this is unfortunately also true for supercomputers. The Xeon processors do the same thing. They lower the frequency when they are not in use. From an environmental perspective, this is a good thing. We don't want them to run at 100% all the time. We don't want to pay the electricity bill for them running at 100% all the time when they are not in use. But for profiling, that actually does create a problem, because they do need some time to ramp up. And so the results can't always be trusted. But TimeIt really tries by generating long loops to provide measurements that are reasonable. And as you can tell here, it does provide error margins. All right. The notebook has a couple of more exercises that you can play with. But I think I'm going to do two more presentations, and then you get actually 2 notebooks to work on.